Hello, so I'm making this video because I've been a bit sick the past couple of days and my voice is still in pretty rough shape, so bear with me. So this is problem 3 in the homework, and it's 1.40 in Schroeder, and there are 3 parts to it. So the first part is asking us to prove that this differential equation relates temperature and pressure as an ideal gas expands adiabatically. So we can start with Schroeder equation 1.40, which gives this relationship between volume and pressure. And then we substitute in the ideal gas law, which we solve for volume, so that lets us deal with only pressure and temperature, which is what we're looking for. And then the next step is to get rid of the C constant, and the easiest way to do this is to differentiate both sides since the derivative of a constant is 0. And as you can see here, I did a bit of algebra to separate the two variables, which left C in for a bit longer. But you can also just use a product rule, like implicit differentiation, so that the C is left isolated and then it will go away immediately. And then I'm sure the algebra will check out in a very similar way. But after the algebra that I did, I was left with a result for dt dp in terms of pressure, gamma, and also that constant C. So going back to this equation relating temperature and pressure, this algebraic step took me a very long time to figure out, but essentially you can get the form T over P by increasing the exponent by 1, which then simplifies the exponent to just 1 over gamma once you add that 1, because gamma over gamma is the negative 1 there. So this is exactly the exponent that we had up here in this relationship. So then after plugging that in, everything we don't want sort of goes away, and then we have this equation relating the change in temperature with respect to pressure, as well as the temperature and the pressure themselves, and also some gammas. So basically all that's left is to remember that gamma is the adiabatic exponent and is equal to f plus 2 over 2, and then just substitute that back in and simplify. So finally we're left with this equation, which is the one that we were looking for. So for part B, the goal is to show that the change in temperature as we increase the height is a constant, around 10 degrees per kilometer in Celsius. And it gives a hint to use the result of problem 1.16b to find the formula for dt dz, which will be the answer. So 1.16b shows the change in pressure with respect to height as a function of the pressure, so that's a differential equation. So the way that made the most sense to me while doing this was just to use this relationship along with the result of part A to essentially eliminate dp using substitution. So you'll notice the pressure and the temperature both cancel out here, which leaves us with an expression for dt dz that isn't dependent on anything except constants, which is good because that's what we were hoping for, that's what we were looking for. So I found values for a lot of these constants online. K is 1.38 times 10 to the negative 23rd. G is, of course, 9.8 meters per second squared. And I found the molar mass of dry air to be 28.9647 grams per mole. But M is the average mass of a single molecule of air, so I had to divide by Avogadro's number, and then divide again by 1,000 to convert to SI units from grams to kilograms. And then the only other value we need is F, which should be 5 because the molecules in the air are all diatomic, so they're linear. So after plugging everything in, I got a value in kelvins per meters, which needed to be converted to Celsius per kilometers, because that's the units that were given in the question. But the thing is that since the scale of Kelvin and Celsius are the same, and we're dealing with a change in temperature, it doesn't really make a difference for that one. So I just had to convert from meters to kilometers, and I got an answer of negative 9.76 Kelvin or degrees Celsius per kilometer. And I'm just noticing now that my unit there still says meters, so I'll have to fix that. But yeah, that's in kilometers there, which is roughly this is roughly the -10 value that we were looking for from the problem. So that's great. And finally, for part C, the goal is to find an expression for the pressure as a function of z, which is the height from sea level. So I started by just trying to set some equations equal to each other like I did in the previous problem, like the previous part, to get an expression for dp dz, and then solve a differential equation, which, as you can see here, did work very well if temperature was treated as a constant, like an isothermal model. The problem was when I tried solving the differential equation using this function for temperature found from the previous part, which I guess I should explain. So basically the temperature is some starting temperature T0, which is at sea level, and then it changes by that constant gamma, the -10 Celsius per kilometer, as it goes up a certain amount of height, which is z. So yeah, basically the equation was too difficult to solve for me because like there was an integral that I wasn't quite sure how to do. Although I've been told that it would have worked out if I kept trying. So if you want to go for it, you can. More power to you. But eventually I found this other way where I can use this separate and integrate method, which I learned in AP Calc. And the only tricky bit here was knowing this integral rule, which I had to find online, which shows that the integral of 1 over b plus ax with respect to x is equal to 1 over a times the ln of b plus ax evaluated at the bounds. So after knowing that, the rest of the problem was just algebra, and the result in the bottom right corner is what I got for my pressure function in terms of z. So the final part of the problem was to plot both the adiabatic model as well as the isothermal model for z between 0 and 20 kilometers. So I just put both functions into Desmos and set the constants to their proper values, and then set the scale for the chart to 0 to 20,000 because it's in meters, not kilometers. And then, as you can see, the adiabatic model is represented by the red line. It decreased faster than the isothermal model. And this makes sense because the temperature is directly proportional to the pressure. So if the temperature is decreasing instead of remaining constant, then we would expect the pressure to decrease faster as well. So yeah, that's essentially it for this problem. If you have any questions, just text me and I can probably answer them. I hope this was helpful, and assuming I'm not sick anymore, I'll see you all in class on Monday. Thanks. Okay, just one thing. I was just going over the video, about to upload it, and I realized that this rule, this integration rule that I had to find online is just a very simple, like, ln is the derivative of the argument over the argument, and so then the 1 over a is just so that the derivative of the argument cancels out, because that's just a. So I just wanted to point out that it's not that I wasn't capable of doing this. I just am tired and not feeling well. And yeah, so I just wanted to point that out, that this is not something that you have to Google. This is a very simple integration rule that I just wasn't like aware enough, or my mind wasn't working well enough to come up with at the time. So yeah, that's it. Okay.